In this video, we're going to look at some operation called the dot product. It's an operation that can be done on two vectors. So we're going to define what the dot product is. We're going to evaluate the dot product and also expressions that contain a dot product. We're also going to use the dot product to find the angle between two vectors to determine if two vectors are orthogonal, to be able to find something called a vector projection of a vector onto another. And then finally, we're going to express a vector as a sum of two orthogonal vectors. So we probably remember that vector addition and scalar multiplication result in a vector. Okay, so if I added the vectors 2, 1 plus 3, 4, that would result in a vector of 5, 5. Okay, and if I took 2 times the vector -1, 3, that would be the vector -2, 6. All right, so those are just basic operations that we looked at in the last section. But the dot product is an operation that results in a scalar. Okay, remember a scalar is going to be a number or a constant in this case. It's really easy to compute the dot product. If we have vector u and v that are comprised of components u1, u2, and v1, v2, then what we do is we just multiply the x components, we multiply the y components, and then we add those together. So u1, v1, u2, v2. So really easy operation that we're going to be seeing throughout this section on the dot product. All right, and then we're also going to take a look at what it's good for. So just some properties of the dot product. We could prove any of these very easily. The dot product is commutative, meaning that the order in which we perform the dot product doesn't matter, which makes sense because multiplication and addition are both commutative. If you dot a vector with itself, it's the same as the magnitude of that vector squared. If you dot anything with zero vector, it is the zero vector itself. If you take c, which is a constant, times vectors u dot v, that's the same as either cu dot v or u dot cv. Okay, so in other words, we just multiply that scalar by one of those two vectors, and then we perform the dot product. And then finally, the dot product is associative. So notice that if we take u and then dot it with the result of v dot w, then u dot v dot w is that same result. Right? So let's just go ahead and find a few dot products. Okay, it's actually pretty easy. We'll see that it's pretty easy operation. So we want to find uv and vv. Okay, so u dot v and v dot v. U dot v is going to be equal to -4, 2 dot 3, -3. And that means what I'm going to do is multiply -4 times 3 plus 2 times -3. Okay, so what I did was I took -4 times 3 and then 2 times -3. That gives me -12 plus -6, which is -18. Okay, so that's all the dot product is. Really easy to compute. V dot v means that we just dot a vector with itself. So in this case, it's going to be 3, -3 dot 3, -3. And in this case, 3 times 3 is going to give us 9. Okay, so it's going to be 3 times 3 plus -3 times -3, or 9 plus 9, which is 18. All right, so that's all we have to do to find a dot product. We could do it with vectors that are in this form as well, where there's a linear combination. So u dot v, again, we would just take the I components and multiply them together. So it'd be -1 times 5 plus 3 times -2. All right, so x components multiplied, y components multiplied, and we add. That's going to be -5 plus -6, which is -11. And then v dot v, that's going to be 5 times 5. Okay, so we're just multiplying 5 by itself plus -2 times -2. Or in this case, that would be 25 plus 4, or 29. Right? So that's all we have to do to find the dot product. Multiply numbers together, add them up. Just a few more examples of performing dot product operations. We have u dot v, and this should be a dot w. Okay, or I'm sorry, u dot v times w, excuse me, because this is going to be a scalar. Okay, so, or 2u, excuse me. So let's start by finding 2u. Okay, so 2u is going to be 2 times 2 comma 3, which is going to be 4, comma 6. Now I'm going to dot that with v. Okay, so that's going to be 4, comma 6 dot -1, -4, or 4 times -1 plus 6 times -4. And that's going to be -4 minus 24, or -28. Now I'm going to take that -28 and I'm going to multiply it by vector w. Okay, so -28 and then 1, -5. If I distribute through, okay, just like we would with any constant, -28 times 1 is -28. 5 times -28 times -5, that should be positive 140. Okay, so that's going to be 140. Right? So that's all there is to it. Not meant to be too difficult for some of these expressions involving dot products. -u dot 3v. Let's find 3v first. All right, since it's in the parentheses. Now 3v is 3 times -1, comma -4, which is going to be -3, -12. And then we're going to dot that with the opposite of u. Okay, so remember that u was 2, comma 3. So -u is going to be -2, -3. And then we just dot these two vectors together. So that's going to be -2, -3, dot -3, -12. -2 times -3 plus -3 times -12, excuse me. All right, so just going through and performing the dot product. This is a -3, by the way. All right, and then finally, this becomes 6 plus 36, which is 42. Finally, if we wanted to go through and add two vectors and then dot that, okay? So let's just work inside the parentheses first. Let's find 2v, right? And remember, we found 2v, we found 3v before, but 2v is just going to be 2 times -1, -4, which is going to be -2, -8. And then we need 3w, right? And we said that w was going to be 1, -5, right? So that's going to give us 3, -15. Now we can add those together. Okay, so we're going to add these two vectors together. And so -2 plus 3 is 1. -8 and -15 is a -23. Finally, we're going to dot this with u. Okay, so this is going to be 2v plus 3w. Now we're going to have u dot that 1, -23. And remember, u was 2, comma 3. Okay, so all the way back up here, u is 2, 3. So I have 2, comma 3 dot 1, comma -23. 2 times 1 plus 3 times -23. That's going to give us 2 plus -69, or -67. Right? So that's all we have to do with these dot product operations. Okay. In reality, it's just basic arithmetic: multiplication, addition, subtraction, etc. Okay. So now that we know how to perform the dot product, and also we went through and we were able to perform evaluate expressions that contain dot products in them, now we can start taking a look at some applications in subsequent videos that involve dot products. Particularly the first one we're going to look at is being able to find the angle that exists between two vectors.